I choose as the title Quantum Games and Quantum Information, and you will see very soon why. What you see here on the first picture is a telescope. And this already alludes to the experiments which Professor Ellis was mentioning, the experiments on long-distance quantum communication. You see the famous stars, they're making some tracks back there, and you see one light beam, and this is a laser beam which we use for our experiments. Let me just set the stage a little bit about the questions we discussed, and I want to discuss with you some of the basic fundamental issues. I don't want to go into technical details, neither experimentally nor theoretically. The discussion goes back to the early days of quantum physics. Just to, again, set the background a little bit, quantum physics was created in the first quarter of the last century, essentially. It was immediately realized that this theory leads to counterintuitive predictions when applied to individual quanta, individual particles, including quanta of light or whatever. This gave rise immediately to discussions between Albert Einstein and Niels Bohr, among others. Albert Einstein is well known to everybody. Niels Bohr was a leading theoretical physicist in Denmark. And one of the basic setups they were discussing is the double-slit interference I show you here in this picture. This was a picture drawn by Niels Bohr about 30 years later in an article where he recalls the discussions with Einstein. And I like this picture very much. You know, I am an experimentalist. This picture was drawn by a theoretician. But he knew that, for example, screws are very important in an experiment. You know, this is not just a coincidence. They're really important. I can tell you from my own experience. If you forget them, it doesn't work. Now, just to set the stage a little bit about the kind of questions these people have been debating and which are still being discussed today, but on a much more advanced level. Here we have an entrance slit. From the left, you might imagine something coming in. Actually, for a quantum physicist, it doesn't matter what. Let's talk about light for the beginning. There's light coming in, and the light illuminates these two slits. Now the light can go through both slits, and when you have an observation screen here, you see dark and bright stripes forming, called fringes. Now, why are they forming? This is easily understood if you know that light is a wave. So at some place where the bright fringes form, the two waves coming through the two slits enforce each other. At the dark places, they extinguish each other. So far, so fine, and we understood everything. The problem is that with quantum physics, as has been first suggested by Einstein and then formulated nicely in theory by many people, in quantum physics, we know that light consists of individual particles, of individual quanta. So if we now realize this, we can ask that we have individual quanta, we can ask ourselves, how do these stripes form then? Because an individual particle can only go through this slit or through this slit. But in order to, for example, make a dark fringe, we've before learned that we have to have waves coming through both slits. So somehow each particle should know whether the other slit is open or not. This is crazy. This doesn't make sense, right? And Einstein used this kind of argument to argue that quantum mechanics can't be the final answer to our understanding of the world. He actually predicted for this kind of experiment. He said, well, there are many particles going through, and they meet each other, and they kind of make up the pattern then, which is a very, very reasonable idea. This is one of the points where Einstein was definitely wrong. We now, today, can do experiments with individual photons, individual particles, one by one, and if we sum up many of them on a photographic plate, we still get the fringes. So how can that happen? The modern way to talk about it is the following, that we talk about superposition of waves, but these waves are not real waves, they are very abstract waves, they are probability waves. They are just a means to calculate what happens. And these waves can extinguish each other or not, but they are not supposed to be something propagating really through the slits. And we get the interference only if there is no information present anywhere in the universe, either on the particle or somewhere outside or wherever, about which path which particle took. So it is something new. It is out of fundamental ignorance about some information fundamentally not being anywhere that something new follows, namely the interference pattern. So this is a very if I might sum up for a second, the debate between Einstein and Bohr is basically the debate between two positions. Einstein wanted physics to explain what exists in the world, and Bohr said no, physics and any other science, by the way, can only be about what can be said about the world. And what is in the world is a big mystery. Now, this was Gedanken experiment, thought experiment, and in the last 20 years there were many realizations with individual particles. Here's an example with neutrons, with massive particles, where these are this is the pattern, these are just the fringes, many neutrons, few, dark, many, few. The fringes which you observe in an observation plane, and these neutrons really come one by one. Usually the apparatus was empty. Sometimes the neutron passes through, and if you collect them all, you get the interference fringes. So Einstein was definitely wrong. By the way, for the physicists, you can use this to test some features of quantum mechanics. As Professor Ellis mentioned, we have done this kind of experiments also with very big molecules. Now we are at molecules which consist of a couple of thousand molecules already. So this is really taking off, and there's no reason why this phenomenon should be restricted to small scales. It is just a question of technological development. Now, I would like to debate a little bit about how far can we go if objects get larger and larger. Can we go to people, or can we go to cats, have them in superposition, or whatever? This has been put forward first time by Erwin Schrödinger, Austrian physicist, who was one of the creators of quantum mechanics in 1935. He wrote a paper where he discussed this kind of burlesque, he called it, burlesque situation. If quantum physics would apply not only to atoms, but also to cats, to hammers, and whatever, then the situation could happen that you have a radioactive atom here which might decay or not. If it decays, it releases a hammer which breaks a container, a glass containing cyanic acid, and that kills the poor cat. If the atom does not decay, the cat is happy and alive. Now, Schrödinger says if quantum mechanics applies to everything, and there's no reason to believe that there's a fundamental limit, then after some time we know that the atom is not decayed or not decayed. It is in a superposition of the two possibilities, just the way the particle is in the superposition of going through the two slits. And then this hammer must be in a superposition of having fallen down or not, and the cat must be in the superposition of dead and alive. And this is clear nonsense. All right? So what do? Instead of now debating all these fundamental questions, whether it makes sense or not to talk about superpositions of live and dead cats, we take this as an experimental program and try to realize quantum phenomena for larger and larger objects. And there are actually ways one can really believe that someday we will see this for living objects. One fundamental point I want to stress now, which is very important in the quantum world, is the following. It's quantum randomness. Consider a very simple situation. Consider a which emits some light here, and a mirror. This is a bad mirror, a mirror which reflects half of the light and half of the light is going through. We call this a semi-reflecting mirror. This is very easy to imagine. It's not anything complicated. But now let us consider that we know that these are individual particles. What is the individual particle doing? It cannot be divided. This is a fundamental feature of all quantum objects. Would it be reflected or would it pass through? Quantum mechanics now tells us that after having met the mirror, the particle is in a superposition of, again, of being reflected or having gone through. So it doesn't know yet what has happened. It just passed the mirror, but doesn't know yet what has happened. But as soon as you put detectors in, which make click when a particle arrives, either this one or this one will fire and tell the particle is here. So at this very moment, it is decided whether the particle was reflected or passed through, and not before. Why can we say that? Because we can bring these waves together if we want and see interference again. So the basic point now is, and this is really very fundamental, that this is objective randomness, as we call it. For the individual event to happen, there is no cause. There is no cause which we just don't know. There is no cause. I like to provoke some of my Catholic friends sometimes. When I talk to them, I say that not even God knows what will happen. And they tell me, how can I say this? And I said, well, just give God the right to have created the world such that it's a little bit more interesting for him or her, He doesn't know always everything beforehand. But this is just a side remark. So just to tell you a little bit, show you a little bit how this works. Here's a photon clicker, we call it. We can use this kind of thing now to build random number generators, which are very important in many applications, like for calculations or whatever. Here's such a photon clicker. It's a photon clicker which consists just of what we have here. We have a half-silvered mirror, we have a source, and we have a detector. And whenever a photon arrives from the outside, I close it, I open it, you register one photon. The point now, whether a specific photon coming in will trigger the detector or not, is completely random. There's no causal possibility for explanation. So let's move on now. Einstein did not like this randomness, and already in 1909 he expressed his discomfort about this sort of randomness, and he actually said, contrary to my position, in any case, I am convinced that God does not play dice. Supposedly, Niels Bohr told him, stop telling the Lord how she should run the world. It is up to the Lord to decide. Now today, and this is the basic message of my talk in terms of application, you just saw an application of this, random number generators. Many of these fundamental phenomena have found applications now which actually are useful in technology. And I keep telling my political friends all the time, if you want us to do something useful, don't ask us to do something which you consider useful. Because the really long-range things nobody can imagine. You have to be open in science for new ideas. Now, the new idea was quantum information. The basic notion of quantum information is the qubit, the quantum bit, and I show you some visualization here which we tried, and I should warn you, one cannot really show quanta. This is not possible. But it's just a matter to help us with the imagination. Here is a representation of a classical bit. Today everybody knows, because we play with computer, that the bit is 0 or 1. Here is a classical bit, it's the switch, which can be 0 or 1 depending on whether it is on or off. A quantum bit would be in a superposition of 0 and 1. It is not that it is a bad switch, but it is really in both positions at the same time. So it would not be 0 or 1, it would be 0 and 1. And now you can imagine that this fact, and it actually can have different amounts of 0 and 1. So you can imagine that this fact allows you to store much more information in a bit, in a quantum bit than in a classical bit. And it allows you new manipulations which are not possible with classical information. And this is the reason why people believe that quantum communication, using individual quanta to communicate, or quantum computation, using quanta as the core of a computer, will result in a new technology which basically beats everything which we have now. Another notion I want to introduce now, besides randomness, is the notion of entanglement. This is a famous paper by Einstein, Podolsky, and Rosen, published in 1935 in Physical review, where they realized that if you have two particles which had some interaction in the past and they are separate, you can have the situation that measurement on one instantly, no matter over which distance, changes the state of the other one. Einstein did not like it, and he called it spooky action at a distance, and he was hoping for a new physics where this spooky action would not exist. One of the co-authors tipped off New York Times, and they wrote this kind of article. Einstein attacks quantum theory, scientist and two colleagues. The other two colleagues were also scientists, but never mind. But I guess if you work with Einstein, you are not a scientist. He's so much above, doesn't matter. Find it correct, even though it is find it not complete, even though it is even though it is correct. And so this shows you how bad some journalists write stuff, even in the New York Times. But this doesn't matter. The important point is that Erwin Schrödinger, I showed him to you already, realized immediately how fundamental this notion of entanglement is. And he says entanglement for him is the most fundamental notion in quantum physics, the one which forces us to abandon our cherished views how the world works. I would like to show you this in terms of a game with a pair of dice. If I have a die here and I throw it, and it shows a 4, how likely would it be that if I throw it here, I also get a 4? Luckily, no, it's a 1. It's not the same number. But imagine now that I had a pair of dice where it's always the same number. Now it's a 4. Next time I throw it, oh, it's again a 4. That's amazing. Next time I throw it, I get a 1. And if I would throw this one at the same time, I would also have gotten 1. This is the notion of entanglement. If these were quantum dice, which you cannot buy yet, but I promise in 100 years you can buy them. If these were quantum dice, they would show the same results every time you throw them, no matter how far they are away. The point now being is that each of these results is completely random, in the way I mentioned before. So how can it be that two completely random events give you the same result? And this is what brought Einstein to make the statement. This is the most important feature of quantum mechanics. You could have two different kind of explanations to help a common sense mind to interpret the things. Interpretation A would be to say, oh, maybe there's a hidden mechanism in both of them, where it's pre-programmed what they will be, and now it's pre-programmed to give 1. Next time it's pre-programmed to give 9 or to give 6 or whatever. So just some hidden property. And the second possibility of explanation would be maybe there's some communication between both. A very sophisticated communication, again an internal mechanism, and this one decides to give the 6, and it tells the other one it will also give the 6. And there's a lot of experiments now have been going on in the last 30, 40 years to rule out these possibilities. And we now know that none of these possibilities is possible. We have to live with the fact that these are two random events which are each completely random in the sense, as we mentioned before, there is no hidden explanation why it happens the way it happens, but they're always the same. So here is just to show you the importance of the paper. These are the scientific citations in scientific literature of this Einstein-Podolsky-Rosen paper over the year. It was published in 1935, and you know the number of citations is a measure how important the paper is. It was quoted only 5 times in the first 3 years, and then it was ignored. So it was a bad paper in that sense. And then it picks off in the 1970s. We have a lot of interest because somebody suddenly found out that you actually can test these assumptions, which I mentioned before, that there might be a hidden communication over there. We really can test them in experiment. This is by a theorem. And then to the big surprise of everybody in the field, we happen to be on such experiments early by chance. To the big surprise of everybody in the field, it turned out that this notion of entanglement, as Schrödinger calls it, became a basic procedure for quantum computation and things like that. Nobody expected that, and now you see that the paper is quoted about more than nearly 250 times a year, which I like to say does not mean that it is read more often than in the old days. But that's a separate story. Bell's theorem, I mentioned, Bell's theorem was the theorem which allows us now to check these kind of ideas, which I mentioned for the dice, whether there's some hidden mechanism. The experiments work with a source, sorry, this is a strange language here, with a source which puts out two photons, two particles of light, which can be entangled such when you measure their polarization with two-channel polarizers here. It turns out that both are either always horizontally polarized or they're always vertically polarized. So two possibilities, not six like with the dice here. And what Bell showed is when you do measurements, when these polarizers are not oriented parallel but at angles, then the correlations between both sides in quantum mechanics are stronger than any such classical explanation. This is called a conflict of quantum mechanics with local realism, that what happens here is local, it's independent of what happens on the other side, and it's some property hidden in the system which we don't know, but it's a real property. This led to many, many experiments which all confirmed quantum mechanics and realism is in troubles. There's a nice article I can recommend to everybody of you, written by John Bell. It is called Bertelsmann's Socks and the Nature of Reality. It's a very strange article for a strange title for a scientific article. What he argues there is the following. There's a physicist, he really exists. He's a colleague of mine in Vienna by chance. John Bell was at CERN in Geneva. And he always wears different socks. As a matter of principle, he never has socks with the same color. So when you see, Bell says, when you see Bertelsmann coming around the corner and you see a pink sock, you know definitely that the other sock is not pink. And the explanation is very simple. The explanation simply is because he put on different socks in the morning. So the color of socks in that case is an element of reality. It is real. And then Bell goes through a very beautiful argument without formalism, without philosophy, where he argues and convinces you, I promise, he convinces you that why in quantum mechanics we say if these were quantum socks, you would get the same result. One is pink, the other one is not pink, but the assumption that the socks had their colors before you looked at them is wrong. And that's the basic point. That's the basic point, that you can have situations where the observation makes, I would not say creates the result. This is already interpretation. Where due to the observation, a system has definite properties, but we know that before it could not have this because this leads to a contradiction. That doesn't work. Okay? So this is the notion of the quest for realities, I would call it. Here are the experiments which Professor Ellis mentioned in his introduction. This is the long distance record for such quantum experiments. We create pairs of photons on the island of La Palma. This is at the Canary Islands, which are about a few hundred kilometers west of the West African coast in the Atlantic Ocean. And we send, of these photons, we keep one locally in a glass fiber, and we send the other one over to the island of Tenerife, where it is caught by telescope, and its polarization is measured. Here's the telescope which we use. This is actually not an ordinary telescope. It's a special telescope. Why it cannot be an ordinary telescope? As everybody of you who ever talk to astronomers knows that their telescopes usually go down to maybe 20 degrees or something. Because if you go down all the way down to the horizon, you don't see much anymore. So it doesn't make sense to build such a telescope. This telescope was built by the European Space Agency to develop optical communication with satellites. And if you want to follow a satellite, you have to be able to go all the way down to the horizon. You don't want to lose the signal. So this is a telescope and they built it for optical communication with standard laser light. We are using this telescope to look over to La Palma to catch our individual particles of light, our individual photons. Here a picture how the setting looks like in there, once if you are there on the islands. This is the source on La Palma. Here's in here we have NOT means Nordic Optical Telescope. We keep one photon locally in a glass fiber, send it around and measure it sometime later after it has been measured, and the other photon is sent over to Tenerife where it is also measured. Okay? Here's a radio link for a special experiment, but that is not important. You can imagine here, this is 144 kilometers, and believe me, when you stand up there, it's really far away. And it always amazes me that one can catch individual particles of light after such a distance. That's a picture I've seen from the OGS, Optical Ground Station on Tenerife. Over there is La Palma. This is El Teide, the highest mountain of Spain, which has an altitude of 3,800 meters. Here's the reception station for our individual photons. As I mentioned, we have tested this entanglement over this distance, and we have closed some loopholes in the interpretation of the experiment of the kind I mentioned before, because you can imagine over this distance, when you measure the two photons, you really can make sure that no signal about this measurement can travel to the other one before this measurement is made. So this is really completely independent. And the other features of the setup, what we do is we have on this side we have a quantum, on both sides we have a quantum random number generator, which decides randomly which polarization should be measured on this photon, same on the other side, and sent very fast to the detection station. The point here is that we want to make sure that the choice, what is being measured, can also not be influenced by the source or by the other side, or that there cannot be any interaction between the possibilities. Now, I want to discuss a little bit the philosophical possibilities which we are left here now. One is that we assume that locality is not true. So in any way, even as Einstein says that nothing can travel faster than the speed of light, maybe the two dice know of each other instantly. The other possibility, which is always a logical possibility, the other possibility is that the world is completely determined. There is no freedom. What is important in the argument of Bell's theorem is that the experimentalist is free to decide what she wants to measure, what feature she wants to measure on the particle. If this freedom does not exist, if everything is completely determined, then we have no problem. But if that is the case, then I ask myself, what am I doing when I do physics? When I do physics, I believe that I can ask free questions to nature to find out something new. If this question is also determined by nature, nature could fool us around, right? She could tell us to ask this question or that question, which is irrelevant or whatever. It would be the end of science, I would argue. Another possibility is that you have actions back into the past, in the sense when you have my two particles, which were created by the source and which are measured, that actually back into the past, the measurement influences the source some while ago and tells us what the source has to admit. This is also very unusual, that you have influence back into the past. Another possibility is that Aristotelian logic breaks down, which is if A is equal to B, B equals to C, then A is equal to C, this kind of simple reasoning. And the possibility which I like most is that our picture of reality is not tenable, at least not the picture which we have in everyday life. It is not fair to assume that what we observe when we do a measurement has existed in all cases before I do the observation. Okay? Now, the reason why I believe that, so the program, the research program in my group has been to try to focus in onto this question more and more with new experimental ideas. One of the experimental ideas is the 5 cups, which I want to play with you now. Here are 5 cups. With 5 cups, and I have 5 dice. Okay? You have 5 cups, 5 dice. As you can see, the dice have different color. They are purple and they are blue. I hope you can see it over there. And the task, a magician is given the task to distribute these. The numbers don't matter now anymore, so don't worry if you cannot see them. A magician is given the task to distribute these dice such that whenever he opens two neighboring cups, he gets two different colors. Okay? Now, let's play the game. I open these two neighboring cups, I get two different colors. Easy, I've won. I open these two colors, I get different colors, I've won again. I open these, I've won again. All right? So it's very easy, right? I open these, I still have won. And now I open these and I have the same colors. So I could only succeed in 4 out of 5 cases. And there's no better way to do that if these are 5. So the classical optimum, we say, is 4 out of 5 cases. Now, quantum mechanics, and this is the next part of my story, quantum mechanics tells us that there are situations, if these were, again, quantum dice, in a very special situation, that sometimes you actually can have in 5 out of 5 cases the same color. So when you cover it, and you look at any of the two, you look at these, you get the same color, they're different, and you would get different here too. It actually turns out that on the average, in 4.5 cases, you get the different, which means that in half of the cases, you get different in all 5, and in half in all 4. Now, I tell you now how we do it in experiment a little bit for the physicists. I know this is now a little bit the harder part, but what is the message? The message is, for the magician, this doesn't work because the color has, these buggers have to carry the color before you look at them. They have to be in there. In quantum mechanics, this is not necessary. You can prepare the system such that the instruction is, your color have to be different, but not telling the particles what color they have to have. Okay? Now, how do we do this? This is now for the physicists among you. How do we do this in experiment? For the non-physicists, it'll be very short. Don't worry. But you can take a little nap now for 2 minutes. So this, what you see here is a sphere, and what this is different directions in space. And there are 5 different directions in space. These directions are pairwise orthogonal. Like A1 is orthogonal to A2, this is orthogonal to A3, to A4, to A5, and to A1. Okay? And they form a pentagram. You can see a little pentagram here. They form a pentagram. And it turns out that if these are the directions along which you measure a spin-1 system, which is an eigenstate to the direction to the center of the pentagram, then the squares of the spin components pairwise commute. So you can measure them at the same time. And the pairs of the spin components just play the same role as the color here. Instead of purple and blue, I have 0 and 1. They commute. And it turns out that I can have a situation where this is a situation invented by Kliashko, colleagues in working in Turkey. You can have a situation where an inequality which you derive from here, assuming that now, more strictly speaking, that the individual measurement results are given by probability distributions. A definite result includes a probability distribution, limit the correlations, and quantum mechanics violates them. How do we do the experiment? Now I can tell again the non-physicists to wake up. What we do is we realize the system such that we have one photon, one particle of light. Remember, we had superposition of the 2 slits. Now we prepare the photon to be in a superposition of 3 modes of propagation. This could be 3 glass fibers or just 3 different beams propagating and so on. And then what we can do is we can play with these two beams. For example, we can mix them with mirrors, or we can interchange them, or whatever you want. And the question simply is the probability to find whether I find the photon here in this beam, which doesn't know anything about what, so the photon could be here or here or here, is the probability whether I find a given photon, which was started long time ago, here, does it depend on whether I manipulate these beams up there or not? The answer must be no. How should it know? This would be silly. Quantum mechanics says no, it depends on whether I find the photon here, depends on whether I manipulate these things here, yes or not. So in terms of our dice, it means that for example, the color of this bugger here, depends on whether I measure it together with this one or together with this one. Okay? So this tells us that systems don't have the properties before we look at them. You can see this as a realization of this beautiful waterfall of Escher. This is a famous picture. You see water flowing down here and flowing down here and flowing down here and flowing down here and falling down. The waterfall is always down, down, down. Each piece of the picture makes sense. In the quantum picture, each piece makes sense, but the all together doesn't make sense. This was actually pointed out by Roger Penrose a long time ago. Now, this quantum idea comes from Simon Kochen, who is now a retired professor of mathematics in Zurich, and Kochen is a retired professor of mathematics in Princeton, and Erich Specker, who is a retired professor of mathematics in Zurich. And this is long ago, and it took a while to develop this kind of experiments. Actually, the idea of Erich Specker was the question whether infuturabilia exist, as he calls them. And now we are again in a philosophical debate. He asked the following question. He's actually a preacher in some church in Zurich. And he asked the following question. This is not serious. Suppose we all show up on the day of judgment in front of God. And God has to judge whether we have done well or not. Then it would be very handy for God to know not only what we did, but also what would have happened if we had made other decisions. And the question is, can God always know that? And Specker's answer is no, he cannot, because in quantum mechanics you cannot assign properties to systems. You cannot talk about the truth value of situations in the whole measurement context, and the whole measurement context exists only once. It's only the context of the experiment which you actually do. So that might help some people to get off the hook on the day of judgment. Now, again, back to possible applications. I mentioned to you that the big surprise for many in the field was that this kind of thing led to applications which nobody expected. And we have the large field of quantum information emerging now. The furthest developed idea is quantum cryptography, where Alice and Bob, they want to share some secret, and they want to communicate secretly. They have a classical channel, telephone, internet, you name it. And in addition, in quantum cryptography, they have a quantum channel which allows them to establish a secret key. And the idea now is the following, that an eavesdropper who can, want to see it again? There you go. An eavesdropper who could have access to all these channels, you don't know to what an eavesdropper has access, would be detected because you cannot observe a quantum system without changing its state. So that would immediately mean that people stop their communication. Here's an experimental realization of this kind. What we did in this experiment was to send a picture of the Venus of Willendorf. This is a very famous prehistoric little effigy which was found near Vienna It's a very famous figure, actually. And actually, it was the first time that a naked lady was pictured in Physical Review Letters, which is the top physics journal in the world. Okay, but this was not our motivation. Our motivation was that my young colleagues came and said, now we want to show this in a nice way, and we want to encode some picture. And they came with a picture of a bomber, something like that, and tell them, you have to find something which is peaceful and which is Austrian. Okay? So what happens is, this is the quantum key. It is established by measuring many pairs of entangled photons. Many pairs of entangled photons, which always give you the same result, each pair, but different outcomes, 0, 1, 0, 1, whatever. It's a big random sequence. And this is the optical representation of about 60,000 bits of random sequence here and here. And because of the entanglement, these two sequences are identical. So what we now do is we mix point by point, we mix this picture with this one, and we get out a random encrypted picture. And because this is completely random, irreducibly random, there's no hidden way how a computer could attack it. This is a cue against eavesdropping. But the recipient can decode it because he knows what the key is. I'll give you another example of quantum computation, just to whet your appetite. There is a scheme. Quantum computation is a huge activity worldwide in many laboratories because quantum computation promises computers which are not only much faster, but which are able to solve problems which existing computers cannot solve. And my personal conviction is that someday we will have a quantum information technology. There is no fundamental reason why it should not work, but there's huge technical challenge. To me, the nicest concept of quantum computation is one-way quantum computation. I try to image this a little bit. These are many qubits, many quantum bits. They could be photons, or they could be atoms in some quantum state sitting in some lattice or whatever, you name it. Okay? And they are all entangled with each other. And then this is how the computer starts. And it's always the same state with which the computer starts. And then the calculation is performed in such a way that the program is nothing else than a measurement sequence. Let me explain. It says, first measure this qubit. What happens is some random result. And what the measurement does, it projects or forces the remaining qubit into a new well-defined state. Then the procedure says, then measure this one, and then measure this one, and so on. And you can form the sequence such that after n steps, the remaining qubits contain the answer to the question which you want to solve. So you tweak the state, you force the system to evolve into the answer of the question which you have. Now, to me, this is quite fascinating. It's the realization of what is called the infinite library, was invented by the scholastic philosopher Raimundus Lullus and put into a nice novel by Jorge Luis Borges, the famous Argentinian writer. Or he also calls it, in the English translation, I think it's called the Library of Babel. It's a library which contains all books which have ever been written and which will ever be written. How can such a thing exist? Very simple. You simply print books with all possible combinations of letters. Now, clearly, this library is completely useless. It turns out, actually, formally speaking, that to find the right book which you want is of the same complexity as to writing it right away. It doesn't matter. It doesn't help. This quantum state is the quantum realization of this infinite library. Because it can be shown that there are quantum states which are universal, which means that they are complex enough such that they contain the answer to any possible question that you can ask. And this, to me, is absolutely fascinating. It tells us something about computation which at least I don't understand yet. Now, I want to come slowly to the end. One of the things which we are playing with is quantum teleportation. You know, teleportation is known from science fiction. Everybody of you knows this word, beam me up, Scotty. I actually saw some of this. I'm not a TV watcher, but I saw some of this with my boys because they like to watch the Star Trek movies. And let me just now seriously analyze what happens. You have an object, you scan the information carried by the object, you transfer the information to the new station where you want them to arrive, and you reassemble the original using this information. Now, the interesting point is that quantum mechanics tells us, because of what is called Heisenberg's uncertainty relation, the first step is not possible. You cannot extract all the information which characterizes the system in quantum mechanics, because the quantum measurement actually changes the state of the system. It's not possible. So it's not possible to do this, and the people who did these Star Trek movies knew that, and for the Star Trek aficionados among you, you know that they invented the Heisenberg compensator to compensate for that. And one of these guys was once asked in a press conference, how does the Heisenberg compensator work? And the answer was, very well, thank you. Now, the interesting point is, like always, quantum mechanics comes to the rescue. Using entanglement, we are actually able to teleport the quantum state, here's an unknown quantum state, over to some recipient. We are actually able to teleport this, even as we are not sending the state itself directly. And this is done using entanglement. We have an entangled source here, which produces 2 photons, entanglement, and entangle the one you want to teleport with one of the 2 entangled ones. There's a lot of entanglement here. But the basic point, I don't want to go into details here, is that you can teleport the quantum state to a receiver station over any distance. Now, this is not a future means of travel, but it is a future means of communication between quantum computers. The future seriously is in space. We are working to put some of these quantum sources on satellites to have worldwide quantum communication, like quantum cryptography and so on, between any 2 stations on Earth. I want to close with some philosophical remarks again. The old question is, how real is reality? You know, many books have been written about this question. Supposedly, Albert Einstein, remember? Albert Einstein, Niels Bohr. Albert Einstein demanded physics to describe reality as it is out there, completely. And Bohr said, no, Einstein can only be about what we can say about reality. Supposedly, Einstein asked one, I was not able to verify whether this really happened or not, but it is everywhere. So it might be, it's a story too good not to be true. The question, is the moon there when nobody looks? Do you really believe that the moon is there when nobody looks? So, to which supposedly Bohr said, prove to me the contrary. How can you prove it? You can only prove it by looking at, including measurement and so on. Okay? So, but there's one interesting point, and I would now like to seriously suggest, in physics we have learned that we should not make distinctions which are not warranted. Very often distinctions which we made are based on our prejudices and our expectations. For example, and when we don't make this distinction, we make a big progress. For example, Newton found out that the same laws which describe falling an apple on Earth, or falling a die on Earth, actually describe the motion of the celestial bodies. So he unified the laws on Earth with the laws in heaven, which was a big achievement. There are many unifications like that in the history of physics. Now, to me, the distinction between reality of information is a similar artificial distinction. This is now my personal opinion, okay? Because we cannot operationally separate the 2. Whenever we talk about reality, even think about reality, we really handle information. The 2 are not separable. So maybe now this is speculative here, maybe the 2 are the same, or maybe even information is constitutive to the universe. And this reminds me of the beginning of the Bible of St. John, which starts with, in the beginning was the Word. And I know that this is not the only tradition in the world which says that, something like that. So in the end, I just want to underline, this is, a lot of this research is going on actually a lot of quantum computation research is going on in classified laboratories. And this proves that the Americans are far ahead of us. This is a parking lot near Washington, D.C., and evidently they already have quantum cars. Thank you very much for your attention.